to the last session this morning. So in this session, we're going to work through in practice some exercises using Mutect2 and related tools called snips and indels, somatic snips and indels. Okay. So yes, we'll need a few things. We'll need the worksheet for today, which is the GTK4 somatic Mutect2 worksheet that is in the worksheets directory. Okay, it should look like this on the front page. We will need our terminal, and we'll need our terminal specifically. We'll be using the same Docker, the GTK Docker that we used yesterday. So you'll want to start up your Docker, just like yesterday, if it's not still running. What else do we need? We are going to need some data, so we can pull up my data directory. We're now today going to be working with the day 3 somatic part of our GTK bundle, which you should find. Which you should find in there, and we'll also need IGB because one of the things we're going to be doing today is looking at a lot of somatic variant calls and discussing whether they look good or not, why they might have been filtered out or not, something like that. So I'm not sure why this is not working for me, so I'm going to take a minute to sort that out. In the meantime, please make sure that you have Docker running, that you have all the resources that you need for this session. Technology is going to make our lives easier, I'm sure, any day now. All right. Tech support. This is why I bring a software engineer with me. right, so I'm experiencing a few technical issues. The computer is restarting and thinking about what it's doing. In the meantime, we can already talk through what we're going to do today in a little bit more detail, which I was going to talk to you about anyway, so everything's fine. Okay, so on the first page of your worksheet, you have a restating of the pipeline that we're going to run. And there's two main pieces, right? Actually, there's the first piece of the pipeline, the pre-processing. I just want to restate that the pre-processing we do at this point, we do the same pre-processing that we do for germline samples. Okay? And once we have our analysis ready bands, we're going to be taking our tumor and normal pair and putting that through the Mutect calling stage. And that's the first thing we're going to do today. And you'll see that the command line is going to be a little more sophisticated than the command line that we have for habitat caller. Some of the arguments that we're going to, some of the parameters we're going to use today are actually meant for exploration and education. I'll point out those that are not actually normally part of the pipeline. And we'll go over in detail on what each means and why we're doing that. Okay? Then, once we have our calls, we're going to review some calls, but we're also going to go over some of the principles in more detail of what we talked about this morning about the panel of normals, how do you make a panel of normals, and how do you filter your calls once you have them. Okay? A brief word about the data we're working with today. We're working with data that is fully public. It's different data compared to yesterday. So yesterday we were using just this whole genome sequence from 3 people from the family, which are public samples. They were for people as such. The material we're using today comes from cell lines that were cultivated. Obviously, they were originally collected from a person's tumor and normal tissue. And these samples are fully consented. So the person who donated this consented to their data being used for technical and development and education purposes. So these are public cell line data sets. Okay? Now, one thing that we do find with cell line data, and this will be even more obvious this afternoon, cell line data sometimes has more dramatic changes than the tissue that you might get directly from the patient, depending on the case. And that is partly because with cell line data you can have an accumulation of additional mutations and changes just through the culturing of the tissue and the preservation. Okay? All right. We're almost there. Got that running. Sorry, I can't quite get talk while I'm doing this on the computer. All right, okay, I've got that running, I've got my container up, so we're ready to go. Thank you very much for putting up the screen. All right, so we're ready to proceed. Let's put that away. So we have our cell lines, as I was saying, and we're going to start by doing the Mutect2 call up front, okay? So this, you should be able, this is a very long command line, and it takes a little bit of time to run, so we're going to start that first. You should be able to copy paste it into into your terminal. If you experience any issues, then you will have to restart. But when I tested it most recently, it was working fine. So I'm in my container here in my Docker. I'm going to move over to the data bundle directory, and specifically to the day3 data. Okay. So as usual, I have some number of directories with the data in it. And so the first thing I'm going to do is call Mutect. And let me show you briefly what I meant by the parameters that we use in the pipeline versus the ones that we're just using here today for demonstration purposes. Let's put that as a more human level. And here we go. Okay, so my command is down here. As usual, calling GTK. The tool is Mutect2. If you're migrating over from GTK3, tiny difference. In GTK3, the T in Mutect is a capital letter. Now it's lowercase because everybody stumbled over that capital T and got it and things went wrong. So now it's just capital M and then everything lowercase, just for simplicity. Just so you know, if you're migrating. For the rest, the reference is given, of course. Then we specify the tumor and normal inputs, the tumor band and the normal band. Now here, this is a little bit different compared to how we used to do it in GTK3 and also in the original Mutect. In previous software, we specified which was the tumor band, which was the normal band directly. Now we just use the regular -I inputs for providing a BAM input to the tool, like every other tool in GTK, pretty much. But we specify explicitly which sample is the tumor and which sample is the normal by referring specifically to their sample names. This does mean that you can have data spread across multiple bands for the same sample. You can also have all of your data in one band. That both will work as long as you and you can also have additional samples. That will all work as long as you specify by the sample name, and this is the value that is in the SM tag in the regroup information. So you specify the tumor SM, you specify the normal SM. Okay? You provide the PON, this panel of normals. So we provide the panel of normals just as a BCF file. And we provide, if it's available, we provide the germline resource. And this is important. This is the resource that contains the population allele frequencies that we're going to use to weigh the evidence, weigh the probability that when we observe something variant in the tumor, we're going to use this to help us, in addition to the match normal, to help us figure out if it's possible that it might, in fact, be a germline variant that is just not present, not well observed in our match normal, but is actually a germline variant that should be discounted from our somatic call set. Okay, so that's the germline resource. And you can see here that in this case, we're using a subset of the nomad resource against HE38 reference. This resource must have the allele frequency annotation, population allele frequency annotation in the BCF. And it can be a sites-only BCF, so we don't need to have genotype information for any samples, just the sites, but it does have to have the AF statistics. And in this case specifically, we're just using data from Formula 17 for this particular tutorial, okay? This argument here, the AF of alleles not a resource, that refers to the allele frequency of alleles for sites that we do not find in our germline resource. So for any sites where we have possible evidence of variation in our tumor results, If it's not in the population resource, we need to provide a default value for the allele frequency that we're going to use. And the allele frequency that we're going to use here, 0.0025, that can be obtained by the kind of rule of thumb equation that Skillet gave, which is that you're basically counting all the samples that are in your resource. You're counting how many samples are in my germline resource. Multiply that by 2 since they're diploid, and we're counting for 2 copies of each chromosome. So we have 2 chances of seeing each allele in each of those samples. So for nomad, which has, at this point, we're working with exome, and in nomad there's about 200,000 samples at this point. And I forgot to put the power on. That's easily seen. My computer doesn't like hearing talking about equations. It's all freaked out. Or I thought it was boring. Anyways, interpret it how you want. Okay, so I was talking about how you divide that number. So I have 200,000 samples in my nomad resource. Each of the samples contributes 2 alleles for each position. So that's 2 times 200,000, so that's 400,000. I think there's a 2 that's added at some point, which is our sample. So that would be 400,000 and 2. And then you divide by that number. And that gives you, and I think we're dropping the 2 there, that gives you basically this number over here. And that is the allele frequency. That is it's kind of an upper value. Like that's, you're basically saying, at most, if I'm not seeing this allele out of a population of 200,000 samples, then that means that it must, if it's a real germline variant, it must be present in at most 1 in 400,000 human chromosomes out in the wild. So at most it would be seen that. Otherwise, I would have seen it in my population. It's kind of a back of the envelope estimate. That's how we get that number, basically. Okay, so that's our heuristic for deriving this allele frequency. Okay, so at this point, we're basically saying if we didn't see the nomad, it's that rare. Okay, now, and you can expect that as nomad increases, as newer versions of the resource get released, we will need to adapt that number appropriately. So this is not a fixed number in time. This will change over time as the resource increases. Or if you choose to use a different resource, you will need to adapt it accordingly. Okay? So that's your AF for things that are not found in resource. And the other common things, the outputs, of course, is something you have to provide. The rest, the 3 other arguments are things that we're only providing that are not part of the default pipeline. The disable read filter here, coming from same config, blah, blah, blah. We'll talk about that a little bit later this morning. That is not part of our production pipeline, and there's a little bit of debate of whether that should be the case or not. And I'll talk about that a little bit more about later. The intervals, that's just the intervals that we're providing to speed things up. In any case, if you are running on exomes, you should always provide the list of exome targets that you're working with. And finally, the BAM out. You are familiar with the BAM out argument. You already used it yesterday in a haplotype caller exercises. We used it to troubleshoot, to diagnose a weird variant column. And here we're going to use it for the same purpose. Now, making the AML does take a little bit more computation and time. Some people argue quite a lot. I have not seen benchmarking on this, but this is not something that is typically done as part of the pipeline. But because it is so convenient to have it for diagnosing it, you can do it by default. If you do it by default, that means that if you want to go back to the data and diagnose some weird calls, this is going to be very helpful. And frankly, I would actually probably recommend doing it because the difference, one of the big differences between germline variant discovery and somatic variant discovery is that for short variants, we have pretty good filtering, scalable filtering for germline variants. We get a lot of variants, but we have, because we get a lot of germline variants out of an XOR genome, we can apply statistical clues for filtering. It's a lot harder to do that in a somatic context because there are much fewer variants, and so you can't really model variant profiles as well. Okay? And so that is one of the reasons that the visual examination of the underlying data is going to be much more important in the discovery process for somatic variants than for germline variants. Okay? And so adding the BAM so that you don't have to go back and regenerate it later is just a good idea. All right, so that was a long-winded explanation. Let's just run it. Okay? And so that's going to run for a little bit. This command is going to do a lot more work than we did yesterday for two reasons. One is that we're running on a lot more data. Now we're going to run this on a full, just about a full chromosome's worth of data, so 17. So it's going to run for a few minutes, probably, because it has a lot more work to do. Yesterday we were running on a much smaller slice of data. The other reason is because if you think about it, when we're doing somatic analysis, there are a lot more things that we have to consider likely compared to germline variant discovery. In germline, there's a lot of things that's at the level of the active region determination we can just dismiss out of hand as probably not something we need to care about. If something has a very low frequency, often we won't even declare an active region. Whereas for somatic variation, we have to be a lot more sensitive to low allele frequency variants, events, and so the active region determination parameters are set to be a lot more sensitive in Mutect than in haplotype caller. That's a big difference between Mutect and haplotype caller, is that Mutect2 is going to have more of a trigger finger for activating, for declaring the region active, compared to haplotype caller. Okay? That does mean that Mutect is reassembling a lot more regions than haplotype caller. Now, to compensate for that, I believe there's some logic that has been built in more recently into the tool, so that we can actually dismiss things that are obviously germline. So there's a lookup to the resource and to the panel of normals that allows you to not have to do it reasonably if you already know that this is going to be a germline variant, because you don't want to do work on that. So that's an optimization that can be disabled, but it is an optimization. That does bring me to an important point that people often ask, why do you not emit germline variants coming out of Mutect? It's doing all this work, it's identifying things that are probably germline. Why not output germline calls at the same time as you're doing somatic calls? And the reason is that the Mutect genotyping model is not appropriate for germline calls. It makes fundamentally different assumptions, much looser assumptions about the data compared to what haplotype caller does. It's a very different statistical model. And so it's not appropriate to use it to make germline calls. Now in the future, what we'd like to do is have a way of having with some tool be able to do both, potentially in some form, to reduce, to economize a little bit, do some economy factors. But for now, it's really important to understand that you have to run these pipelines separately. Just running somatic will not give you appropriate germline costs. There will be some things that look like germlines, but you shouldn't use them as germline costs. I think there might be some plans, they've had some plans to allow admitting things that are dismissed as germline, but it will come with some strong caveats about what you should or should not do with it. Okay? All right, so command, bring that whole right. Okay, so now our Mutect2 job has completed. That output. And please interrupt me with questions at any point, by the way. Any questions about what I babbled on about for a little bit there? No? Okay. All right, so what I omitted here, put it a little differently. So what we produced a somatic, VCF with somatic calls made by Mutect2. That's the first output. It's gzipped, and it has its tabix index right there. And we've also output a BAM file. That's the BAM out that you expect, since we passed in BAM arguments. And you can see that it says tumor_normal. So that's interesting. Let's have a look at what's in there. Okay. I'm deviating a little bit from the worksheets, but I like to look at what I produced when I just finished producing. So I'm going to use IGB for that, and we're going to look at the files that we just produced. Now, for this set of exercises, today's exercises, we're using a different reference genome. These are newer exercises that have been made with the newer genome reference, which is a good thing. Sophie and my team put a lot of effort into dragging us into the 21st century. So I'm going to load the genome profile, but we're going to go grab the reference genome files that are in the somatic bundle, and specifically should be in ref, and I know where they are. It's coming. I'm in a different copy of it. Doesn't matter. Okay. So in ref, you should find Homo sapiens assembly 38, which is our human genome 38, HG38, also called GRCH38 because why not have a bunch of different names for the same thing? Okay, so now I have my human genome reference loaded. Let's load two things. Let's load our VCF that we just produced, and let's load the BAM. The worksheet has you been doing this a little bit later, but let's do this right away. Make sure you go into the day 3 somatic level. Sandbox, of course. So that will open my VCF here, and we'll look at what's in there in a minute. And I'll also open the BAM file, BAM out. Alright, and the data should be close to 17. Okay, we have some data. All right, so if we zoom in a little bit, we see that we have First here, in my VCF track, I have two samples. I have two samples in my VCF. I can verify that also by looking at the text file. Okay, so that's not what I want. If I look at the text file in the results that I produced, so you see the output is a regular VCF, just as we've worked with previously. Okay, and it has records, same as we've been used to. There are a few differences compared to the germline VCFs that we produced with Mutect2. Okay, let's have a look at a few of these differences. One of the differences that we notice right away is that you might notice this. There's no qual score in a VCF that's emitted by Mutect2. Okay, Mutect2 does not calculate the qual score. The qual score describes something that is really intended for germline variation. For somatic variation, it doesn't really make sense in the same way. And so we do not have a qual score. There are other annotations and scores that we use instead that have an important role to play. The main one we're going to want to look at is the T-log. T-log is the log odds of the tumor. And you'll have a score for that. You'll also have a score for the normal. The normal has a log odd score. And these scores together are what Mutect is going to be looking at when it's making the judgment about whether to emit the site, to call the site a somatic variant or not. Because you're measuring the likelihood based on the evidence, the log odd score of this being produced by a germline event versus a somatic event. And it's in part the ratio between them that is going to be important. So we want to have low probability that the data is explainable by a germline variant, and a high probability that it's explainable by a somatic variant. That's ultimately what it comes down to. There are a few of the usual notations that you're used to seeing, like the depth, DP. But then you'll have some newer ones, like in the genotype fields. We're going to have a lot of annotations, including the allele frequency and then the orientation. The F1R2, F2R1, those are counting the number of reads and the read orientation, because read orientation is statistics. It's one of the key pieces of evidence that we're going to use for some of the filtering. Okay, so that's what a record looks like. As I mentioned, we do have we're always going to have two samples in our VCF when we're running in the tumor normal mode. You have the normal sample and the tumor sample. Their name doesn't have to say tumor or normal, but it is helpful since the first part is often the same sample name, and then you say which is normal, which is tumor. And for each of those, you will have a genotype that is given. So the first one that is listed over here is normal, so it's been genotyped as 00, so it's home ref in the normal. And then I have a 01 genotype in the tumor. The tumor is always going to be genotyped as heterozygous. Okay? You're not going to see it be homozygous variant. Even if there's all the reads that support it, the way the modeling and the coding works for how we signify that we have a somatic variant, the tumor is always going to be denoted as a het genotype, which makes a lot of sense if you think about what it represents biologically. Okay? All right, so that's your basics of what your Mutect2 output looks like. All right. You have this quite somewhat strident warning that is in the VCF itself. We consider, and this kind of ties back to one of the questions we had earlier. This does say very clearly, this is an unfiltered call set from Mutect. It is important to run filtering for remove false positives. This was actually added because we realized that a lot of people were getting their Mutect2 calls, and if they were used to Mutect1, the original Mutect, they were used to having that speed definitive analysis ready call sets. And so we've been trying any way we can to make it clear that Mutect2 expects that you will do some additional filtering, and there are a lot of false positives. This is expected. It's not about it's a feature. It's to allow you to have more freedom and flexibility in how you do the filtering. Okay, so that is the basic, basic makeup of our somatic Mutect2 VCF. Now in IGV, what this looks like is that I will have two sample tracks, sample genotype tracks. So I have one variant call that's here in the site level track. Then I have two genotype tracks. In this case, the normal is indicated appropriately as homozygous reference, and it has some attached statistics. And same for the tumor, except the tumor is denoted as heterozygous. And I mentioned tumor, if it's called somatic variant, will always be denoted as a heterozygous. And you can see that it has not been filtered out. In fact, there has not been any filtering, and we do not have a false score. Okay? So that is and we also don't have a GQ compared to germline. We don't have genotype quality as a concept in the Mutect2 output. But we do have a number of other statistical statistics that are recorded and that are going to be used, that can be used for filtering. Okay. So if we look at in addition at what we have in the VAM route, you can see that the first set of reads here, if you remember from what we did yesterday with haplotype calling, the top reads that are kind of this pastel color in haplotype in the VAM route, and that typically for a wide enough active region, you see it span the entire active region. These are the artificial haplotypes, right? That Mutect as part of the assembly mechanism, just like haplotype caller, assemble these possible haplotypes to explain the data in the region. And in fact, I'm not sure if we made that really clear, the code, the underlying code in the GHK that does this is the same for Mutect and for haplotype. It's the same code that does the active region determination and the assembly. They have different parameterization to be more sensitive for Mutect, but they're ultimately the same machinery. It's only after, once you start evaluating what's on the haplotypes, that the two programs diverge. Okay? And so here you have a number of, so I should add also the way the reads are colored. You see that these top four of the four different colors, those are, like I mentioned, the artificial haplotypes. The other reads on my screen are colored according to which haplotype they support. Now, depending, you might not be seeing that yet, because we haven't set that up yet for you. But there's basically an option where if you right-click or control-click, you can choose how you color the alignments. And here I'm coloring alignments by tag, because the tag, the haplotype color tag, or in this case the mutex tag, is what tells us what read has been determined to encode which haplotype. And so by doing this, I can get that coloring. Okay? And this is the tag we're looking for. And because, so I know this is Mutect2, we're not haplotype color, but because it's using the same underlying machinery, and haplotype color was first. That's why the tags that Mutect uses are named after haplotype color. It's HC for haplotype color, even if you're running with Mutect. And that's just because haplotype color was made first. Okay. So this tells me that this set of reads were decided to support this, which is a reference haplotype that does not have any evidence of changes. I have a few others. I have one here that supports the variant haplotype. And that seems to be it. I have a second one. So to make it easier to see that, I can click on it, control click, and you can group alignments. And here I'm going to group by allele. This allows me to sort. Now I'm sorting the reads by tag in the same way that I'm coloring them, which makes it easier to see that I have a whole pile of reads that are supporting reference. I have 2 reads that support this haplotype, which is based on this little G allele here, although it's not very convincing, it's not actually. And then I have 2 real reads that support this artificial haplotype. And here it's just 1 read and 1 haplotype, so that's why this was probably pointed out as not being very likely at all. And you might wonder, why are some of the reads gray? So the gray reads are the ones that actually are considered uninformative. For various reasons, there are conditions where we see that these reads do not help us decide which of the haplotypes is more likely. So if we're not sure which of the haplotypes is more likely, we just don't count those reads as part of the calculation as regards a particular haplotype. Okay? So we're not able to identify specifically which haplotype is supported, so we're just going to ignore that. Okay, so now that's one way to look at it, but if you recall, and maybe this is troubling you, but if you recall, my file is tumor_normal, this is layout. So who do these reads belong to? Do they belong to the normal or to the tumor? Right now I don't know, but I can change the way I'm viewing the data and grouping them. And I can, in fact, if I want to group by sample instead of tag. And now if I group by sample, I'm going to see here if I click on this. This belongs to the normal sample. And lower here, under this separating line, I have all of the reads that belong to my tumor. So now we can view separately what do I have for my normal sample versus my tumor. I see that for my normal, I don't see any trace of this A. All of my reads are referenced for the normal. And now for the tumor, that's where I see the support for the this variant. So out of all the reads that I have, all my normals are referenced, but my tumor reads, 2 of them have this allele. So this is pretty flimsy, right? I only have 2 reads out of all that. In the germline context, we would just say, oh, that's an artifact and get out of here. In the somatic context, if we want to be very sensitive, we are going to accept that and say, okay, I will omit it. Honestly, it's so low that it's more probably an artifact at that point. But I can't dismiss it because it is possible that it's a low frequency event. And so that kind of thing is what in your Mutect output is potentially part of the false positives that are going to end there that you might need to filter out. But just in case, we give it to you, just so you don't miss it in case it's involved. Okay? So that's kind of how you see the difference between the normal and tumor in IgE in your Mutect output. Okay? Or just a randomly selected site. Are there any questions at this point? About the Mutect's behavior, about how it tags things? I'm going to take just a second to get some water, and then we'll continue on with the next part. So that's what came out of our Mutect command. The next thing, and I've already gone over the normal tumor and so on, I just want to make a few notes about something we're not going to run ourselves today, but that you could run as an exercise on this data, which is the tumor only. In some cases, you only have a tumor sample. For example, in cases of blood cancer, in many cases, you do not have a matched normal. And so if you don't have a matched normal, you can still run this. And you can still run this command, except what you would do is, obviously, you remove the normal. You remove the definition of which is the normal sample. Hopefully you still have the germline resource, which is going to be even more important. If you don't have a matched normal, you're really relying on the population resource to eliminate as many as possible of the germline variants. Okay, so that resource is going to be super important, and I think we can expect that as the size of the Nomad collection grows, and any other similar resources that get produced as a result of the many genome projects that we see happening worldwide, hopefully as many as possible get made publicly available so that we can integrate them into these resources. Because as these resources grow, and as our catalog of human variation grows, we'll be able to eliminate more and more of the germline calls from tumor-only call sets. Okay? Because that's how we're going to get rid of what's germline. That's our main way of doing it. That's still not going to eliminate everything that's germline in your tumor-only sample. And in fact, if we do the test of how many calls do you get, if you run this command, and if you compare on the full set, with this command, with the panel of normals, which is a good, reasonable panel of normals, and the population resource that we have, this is the difference in the amount of calls that Mutect2 will generate. Okay? This is what you get with your matched normals. This is what you get if you don't have it. Right? It's a huge difference. So here you'll still have to do some additional work because there are some things that you'll still need to eliminate from your call set. And so it's going to be very important to work with. Okay? So, I already talked about the population resource and how we calculate that allele frequency of alleles on the resource. Are there any questions about that? I thought I saw a hand, but maybe somebody was getting their hair. Okay. So we talked about that. If you don't have a population resource at all, we have just a default value, and that default value is based on the normal expected heterozygosity improvements. Now let's talk a little bit about the panel of normals. The panel of normals is what we're going to be relying on to remove artifacts. For example, here, I'm not saying this is an artifact. I haven't looked very closely at this site. This is a site that I just chose randomly as we were starting up. This is very low frequency. We have 2 reads. With just 2 reads out of the file, it's very possible that it's a technical artifact. Some technical artifacts are things that occur recurrently in many samples and are just due to sequencing context or biochemical events that are somewhat predictable. And so that's what the panel of normals is going to help us eliminate. Because if you have a whole bunch of other samples that are sequenced, generated with the same technology, you expect some proportion of them to be subject to the same systematic artifacts. Now, some of those systematic artifacts might be caught by base quality score calibration in pre-processing, but some of them will still get through. And so the panel of normals is how we're going to get rid of that. If you're trying to make your own panel of normals, there's no one-size-fits-all rule. Generally speaking, in the past recommendations we've given is that you try to get samples that are healthy individuals, or at least not cancer patients. You try to have these be generated with exactly the same technology, including the same lab preparation, the same kits, the same sequencing machines, things like that. Is what we're trying to root out specifically things that are caused by those elements. Try to keep all of that the same. If you don't have access to that, then what you do is just try to get things as simple as possible. A pawn that's not perfect is better than no pawn at all. Okay? And you try to get at least 4 examples is the rule of thumb that we give. Okay? We have a few examples of the command lines in the worksheet of how you actually do this. How do you actually run this? We're not going to run them here because we didn't give you the data to do it. I'm trying to save a little bit of time. But basically, it's a little unfortunate that the command is split into here. But you're really just doing the same thing as I was explaining for the tumor-only mode, except you're running that tumor-only mode on your normals, on each of your normals, in your panel of normals. And so you would provide the BAM file from the normal. You would say tumor is the sample name. And I know it's not a tumor, but we're pretending it is. And the rest of the parameters should be the same. Any parameters that affect how Mutect works should be exactly the same for your panel of normal samples as you apply for your actual tumor case samples. That's very important. It should be the same parameters. All right? And so once you have the VCFs from all of those, and you can do all of that in parallel, you can do it just per sample, so that's pretty straightforward. Once you have all of that, then you run this tool called Create Somatic Panel of Normals, and that is going to apply some combination rules to extract the sites that are in at least, I think it's 3 or 5, there's some rule like that. It has to be in at least several samples. And at that point, then, well, it's 3 since we're doing this sample example. And it'll output a sites-only PCF. And it's just a regular PCF with sites with no genotypes. Okay. So that's how you would do it. And you're more than welcome, honestly, to try that on your own data when you go home. Okay, so now that we've talked, I've talked in some detail about the basic commands for running Mutect, we're going to look at the other big part, which is how you filter the outputs of Mutect. And I'm going to take a little bit of water again. Right, so there's a number of annotations that we're going to look at. I've already gone through the basics with you. Khalid explained some of them in his talk earlier this morning. The main things we're going to be looking at are, and this is not, there's still a lot of work that's happening on this. Okay, so some of this is still kind of the beta form of the pipeline. I would say that the filtering is where a lot of the development is happening right now to try to refine how we filter to really push our ability to provide highly sensitive results while still reducing the amount of false positives. And the science of this is not settled. So a lot of what I tell you is the current thinking, as much as possible. I can't guarantee that they haven't changed their minds since we talked last. Okay, base quality is obviously very important, and it's used in the Perry-Chilin model that's used for the Bayesian calculations that Khalid showed you, which are how we calculate the T-logs, the tumor logs, and the normal log. But we also emit a couple of summary statistics that we don't internalize, which are things like the median base quality of the bases that are supporting each of the alleles. And that is kind of similar to what we do with the base quality rank sum application, for example, on the terminal side. The idea ultimately is to give the analyst the opportunity to evaluate whether it looks like there's an imbalance in the evidence or in the quality of the evidence for the variant allele versus the variance. We also look quite a lot at artifacts like the strand orientation, because we know that when we have only support, we have support for variant allele only from reads that all read in the same direction and not from the other direction. That's a very common sign that there's some kind of artifact, probably some PCR-related artifacts. And also G read count. These, as you can see, it's going to count the read pairs that are in specific configurations that have a skew in which alleles they support. And that refers specifically to one of those pre-adapter artifacts that we were talking about earlier. That's one of those pre-adapter metrics related to the statistics. Okay? At this point, we come to the part where I talk to you about the read filter, the mates on same config or no mapped mates read filter. Okay, that's a long filter name. Internally we call it the Moscow feature filter. Moscow or mate on the take the abbreviate the letters. So the Moscow read filters it's meant to filter out reads that do not fit this criteria. So that if you have reads where the mate is on a different chromosome or it's just not mapped, we can discard them. In a germline context, when we see reads like that, we assume that there's just a mapping issue. Something's in the wrong place, and so they're not informative, and we're just going to ignore them. However, there's some discussion, and one of my team members is quite adamant about this. There's some discussion that this filter is potentially eliminating reads that are legitimately mapping with a mate that's in a different place or different orientation because of some other events, some other variation in the genome. For example, if you have a structural variation event in the same genome, then all the reads in the affected region will have a mate with something that looks inconsistent with this. And so what happens here is that if we rule out reads that are in that situation, we might be ruling out reads that do support real variation, that are just complicated by the presence in the same genome of another type, more traumatic type of variant. And so there's some discussion as to whether we should, in fact, not filter those reads out, but maybe filter things out in post-processing. And again, somebody on my team has done some analysis that suggests that we should probably revise that in some way. So in terms of the tutorial, we just wanted to give you that information that while the production pipeline has this read activated, it's something interesting to look at in your analysis, and that you should potentially make improvement. Okay? All right. Any questions about that? No? All right. So let's actually filter our call sets and then look at what comes out of it. Okay. So we're going to have two steps and two tools here. We're going to, and this is going to allow us to do cross-sample contamination step. This is the filtering we're going to do for this particular workshop. We're not going to do the pre-adapter metrics filtering again because that is currently being overhauled. So we're going to focus on cross-sample contamination. And here I want to make it clear that when we talk about cross-sample contamination, it's specifically the kind of contamination where, for whatever reason, it can be the experimenter who was a bit sloppy, or it can be at the level of even collecting the samples and preserving the samples. Humans are not perfect, humans are not machines, and even machines have some capacity to be contaminated. And so we see that in pretty much all samples that go through our pipelines, through our facility, there's always some small amounts of sample contamination. And this is something we started worrying some years ago because there was one project in particular, and I'm not naming names, but there was one project in particular that had extremely high levels of cross-sample contamination that caused severe problems in the analysis. At the time, there was a lot of analysis that was done and a lot of handwriting, but out of that came a lot of development to detect and compensate for this cross-sample contamination. Now, most of the contamination that we see going through is very low level, and in the germline context, is not a problem at all. Again, in germline calls, if you have a tiny little bit of contamination with somebody else's DNA, it doesn't really matter because the allele frequency is not sufficient to impact the calls. However, in the somatic context, it will impact the calls because we are looking for very low frequency events in many cases. And so this is a method that allows us to detect this and adapt our analysis accordingly. Okay. So we're not going to be removing contaminating reads, it's impossible, but we are going to at least have an accurate estimation that allows us to know what is going to be the limitation on our sensitivity to low frequency reads. Okay, so the way it's going to work is we're going to run this tool. It's called Get Pilot Summaries. We're going to run that on our tumor band. So we're not running this on ECF, we're going back to the original band file and running on that. And we can do that in parallel to the other process that we do. And what's going to happen here is that we're going to look at a subset of sites from our population resource. Specifically, we're looking at common sites so that we don't have to look at too many sites. We don't want to have to do too much work, just enough to find a satisfactory number of informative sites. And so we're going to look at the subset of sites, and for each of those, we're going to do basically a fast genotyping. Fast on-the-fly genotyping, no reassembly. This is one of those cases where you can do kind of quick and dirty genotyping to get a sense of what is the genotype of the person, and we're looking for germline events actually in this tumor. Okay, and we're going to be looking specifically for homozygous variant sites. So we're going to look for each of these sites. Is our patient, is our case sample homozygous variants? For those where we find that they're homozygous variants based on showing at least, I think numbers, at least 80% of the allele frequency is a variant allele, we're going to choose those and run on those sites in the next step. And extract, what we're going to extract is going to be the read counts, the allele counts at those sites. Okay? So we're going to run this finally after all this talking. Sorry there's so much talking. But we're finally going to run some commands again in hands-on way. So please take this command if your computer hasn't fallen asleep. We're going back to our terminal. We're going to run this command. You get a nice little red summary that warning that it's a beta tool. Many of these tools are still, for some reason or another, in beta status. What we mean by beta status is that they're okay to use, and certainly we use them for research. So for research purposes, we're very comfortable using these tools. We believe in them. We think that they're doing a great job. What we mean by beta and by not ready for production is that these are not tools that we would be comfortable running in clinical diagnostic setting. Okay. So that's what we mean by that. The level of validation that we're going through is not yet sufficient for us to be able to say we can run that and not any problems. In any case, for liability reasons, we don't give any guarantees. The software is provided as is. Don't sue us, please. But mainly, that's what beta means when we talk about that. Okay. Okay, so this should run really quickly and provide a summary of pilots at the interested sites. So let's open that up. Alright, it's just a table. I'm just going to open it in my text editor to take a quick look. It's tab separated values, very simple format, very easy to work with. And you see that what's in this file basically, we have the config, we have the position, and then we have this little offset, but the count of reads supporting the reference, count of reads supporting the alt, and the count of reads supporting something else, some other allele that's present, but not genotype as such. And that's your actual low frequency for that halt. And so we're going to be looking at these, so that's for all of the sites that is in our population resource. And so in the next step, what we're going to be doing is identifying specifically sites that are of interest. For example, if I'm looking at this down here, let me scroll up a tiny bit. For example, if I'm looking at this line right here, I have 23 reads that are alt, but one read that is ref. That means I'm very probably a homozygous variant for the site. But I do have one reference read. And when I have a reference read like that at a site like this, I think, well, that could be a contaminant read. That could be a read that comes from somebody else. It could also be mismatched, but that is one of the possibilities. So we have another one with the same case, and that might just be the same, that's probably the same read since they're really close by. And then here, for example, we will have some sites where there's no reads. And so we'll take that subset of all the sites that show evidence of being probably homozygous variants, and then evaluate based on how many of these potential contaminant reads, what is our rates of contamination, estimated contamination in the overall thing. And that's how we get that result. So the tool that will make that calculation is called Calculate Contamination. We believe in having very straightforward naming for the tools. Some software developers like to come up with smart or cute or funny names for their tools. We are boring intentionally because we believe it's nicer to be able to know what the tool does by looking at its name as opposed to having to Google it. Not to target any particular software, like, I don't know, software named based on clothing. There are some. I disapprove. I'll see it on camera. Anyway, so our tools are boringly named, but they are very convenient in that way. It's strongly in that. So now they're running calculate contamination. We are providing as input the table of item summaries, and we are outputting a contamination table as such. Okay? That should run very rapidly. It's an extremely simple calculation. Yes. Okay, and that is really just one line. I don't believe you can run this on multiple lines, but anyway, that'll just give you one line. The reason it's a table format is as opposed to just outputting a number of this, so that we can read this in context of an automated pipeline. Okay, so at the level of looking at the entire RAM that I provided, my level of contamination is about 1.8%, almost 2%. That's not bad. That's kind of normal low-level contamination. And this is my error. This is my degree of error based on the variability that I found across the whole day. Okay. So that's your results, and that you will provide in the next step to the filtering tool. Okay. So to apply this, we're going to use filter Mutect2. And the most basic thing that you should always do for filtering, it's not the only thing you can do for filtering, but it is the most basic thing, and you should always do it, is this cross-sample contamination filter. In this case, we're giving this tool our VCF of Mutect2 calls that we generated earlier, much earlier. We're giving it our contamination table, which is what we just calculated just now, and that will give us our filtered DCF. Okay. Now, as usual in GATK, when we're talking about filtering things, we're just talking about adding a filter annotation. We're not going to remove any sites, anything from the DCF. We leave everything in there and just annotate them. It is possible to get things extracted and removed, but by default, it's all in there. It's just time. Right. So open that. It's compressed, of course. And here we go. Now we have this one. Here's passing record. So this record, we've decided there's nothing wrong with it. We're happy with the call that we made based on the filtering that we gave it. We have a nice high T-Lot of 14 that is well above our threshold of 5.3. We have very clear evidence. We're quite happy with our determination that this is a variant. And we have, if we look at the allele depth for the variant in the tumor, we have 7 reference and 5 tumor. That's great. That's good in terms of the evidence. And because it's high enough, it doesn't get impacted by the contamination-based filter. I didn't really talk about how that was applied, did I? Well, let's look at the next record here. If I look at that record here, I see that this one has something in the filter field, which conveniently is underlined in red by my text editor. That's very convenient. And you can see I have 2 things. I have contamination and I have T-Lot. Okay, contamination, it got dinged somehow. It fell below our threshold, because when we applied a contamination filter, we decided that its allele frequency was too low compared to the level of contamination that we have. Our level of contamination is basically acting as a lower bound of the frequency that we can consider to be reasonable to detect. If I have a 2% contamination rate, that means anything up to 2% could equally be a real variant, or it could be a contaminant. So I'm going to have to disregard that. So I'm not, if I have 2% contamination, I'm not going to reasonably be able to detect events with a lower frequency than that. I mean, they'll be in there, but I will have a contamination filter that says this could just be a contaminant. That's why you want to keep your contamination low, because if you have higher level of contamination, then that limits you even further in what you can reasonably expect to detect. Okay? But you'll notice that it's not the only thing that is appearing in the filter field. I have T-Lot here. And if I look at a few other variant records, I actually have other filters that have been applied. So I kind of glossed over that, but when I applied this command here, even though it looked like I was just passing in the contamination, filter Mutect calls also has a number of things that it filters on by default. So if you were to apply it just by itself, it would apply all the standard filters that we recommend with standard thresholds. Now it's possible to deactivate some, and it's possible to modify the threshold values that you want to apply. And I encourage you to look at the documentation for the names of the parameters. Just each of the annotation has a corresponding parameter. You just specify it and you say, I want to override default behavior. It's very simple. But it's important to be aware by default when you run this, it's going to run all these default filters at the same time. And that is why in my VCF we have a number of variants that are actually filtered out. Okay? And so, where are we on time? Okay, so we have about 10 minutes left. For the rest of the time, we're going to look at a few other variant vectors and try to understand when these filters were applied. Can we identify in the data the reason why they were applied? And based on that, we can discuss whether we believe that the variants are real variants or not. Okay? So now we're going to go to IGB, and we're going to run the final few instructions that are in the worksheets in section 2. There's a little bit of advice for setting up your IGB to do this appropriately. So we've already loaded the unfiltered VCF and the output BAM. We're going to remove the we'll actually delete the unfiltered VCF. We'll add the filtered VCF that we just added, and we'll also add panel normals, the nomad resource, and if we want, we can add the tumor normal. But really, if we have the BAM out, that really has most of the information we want from BAM. In fact, it's more appropriate than these two, since, as you remember from the exercise yesterday, this is representative of what the variant caller actually used, as opposed to this, which is the before the assembly state of the data. Okay? So we'll load the two resources, the filtered VCF. And the resources, the pawn and the population resource, are in the resources directory of the bundle that he gave you. So you'll want the AF only nomad and the M2 pawn. So now we have several variant tracks. At the very top, we have the raw calls. The next one, which also includes each of the samples, right? On the next one, you have the filtered calls. Then you have on my screen the nomad resource, and then finally the pawn. And then below is the tumor normal. And it will be helpful, remember to do this, to color by tag and group by sample, okay? And these instructions are all given in the worksheet right here. Okay, so we're going to go look up this particular site at the coordinates that are given in the worksheet. So you'll want to copy that. Take it into IGB and look that up. Okay. And here I'm going to squish the display of the nomad resource because there are a lot of calls in there. Okay, let's zoom in a bit. Now that I'm zoomed in, I don't need to have it quite as. Okay, there looking at this site in the middle here, I'm also going to squish the display of the BAM files. Okay, for now. Okay. So here you have, it's interesting, right? You have a site that we called originally, and that we did not filter out. I'm going to put that here. And if I look at it, actually, I'm going to unsquish, expand. If I look at my normal BAM file, there's no evidence of variation in the normal. And in the tumor, all of my reads are variant, which, to be frank, I find kind of weird. But this is a very striking difference. Okay, so as far as Mutect2 is concerned, this looks great. It's in the normal, it's not in the tumor. But to be honest, I find it suspicious that it's completely homozygous in the tumor, but it is a site that you should take into consideration, considering the evidence that we have found. It's also not in the tumor BAM. Where's my? Where's my? There's also nothing in Nomad, and there's nothing in the pawn. So on the face of it, it looks like potentially a real site, but there's some discussion to be had about whether that's likely or not. In the interest of time, I'm going to zip by though, but that is the kind of complication that will arise. Okay. Now, the next site that we want to look at, I just don't want to get into that too far, because I want to look at a few different ones. Okay, so now I want you to look at this other site that's the first in the list in the worksheet that is given. And if we zip to here, we're looking at an indel. In this case, so we're looking at this indel right here, but you see that there's a lot going on in our both nomads and in our pawn in this region. Okay, it's a little bit complicated, but you can see that there's multiple events in proximity. There's this big deletion that seems to be present in the normal, right next to it, kind of overlapping. And then there's this other potential deletion that we're looking at. And so this is the kind of difficult context that will happen as well, where we are going to filter out, because if we look at the evidence, we have this variant is showing up in the panel normals. That's a red flag. It's showing up in the normal, so it looks like it might be an artifact that's also in the normal. It's showing up, it's falling below the allele frequency cutoff that is based on our contamination rates. And on top of that, there's the central STRs in this area, short-tanded units. And so this is something that could be explained by artifacts better than as an actual somatic variant. Okay? Now we can look at, let's look at this last one on this page 9, and then we'll have to finish for this morning. Just want to look at this one. Now this one, when you see something like this, it's very colorful and RGB. That means that the assembly that Mutect2 was a mess. Like the assembly graph had a huge number of possible paths going to it. Well, this large number of paths compared to what you can easily expect. And so here, what we're seeing is just a lot of sequence complexity. There's a lot that's going on both in this sample, in the normal itself, and in the tumor band. The proximity of so many other events, other SNPs, things like that, the amount of things that have been reported in NOMAD as well, this makes us think that it's probably an artifact. It's more probably an artifact. And so these are all the kinds of things. And you can see it coming up in the pollen too, in the panel norms. And so when you have this kind of complexity, it is a lot more likely that you have an artifact compared to a real somatic variant. And so this is the kind of thing, fortunately we're out of time for this morning, and I'm sure everybody's looking forward to lunch. But this is the kind of thing that you're going to have to deal with when you're looking at somatic short variants. And Mutect is going to try to do as much as possible to identify this. And the filtering will help a lot, because as you can see, something like this gets filtered out. But there will be cases that are more ambiguous, and that will require a lot of manual review. And hopefully, this gives you kind of a jumping off point, but there will be a lot of work beyond that that you can go on. Thank you for your attention. We're going to break for lunch. It's 12:30. Let's come back at 1:30. This concludes what we're going to do for somatic short variants. We'll see you again at 1:30, hopefully reinvigorated, and we'll be talking about copy number variation first, and then the upcoming new methods that are being worked on that Steve is going to be. Thank you very much, and see you in a minute.